Hello, good evening everyone. Welcome to the class of coordination chemistry. This is the lecture number 1. In the upcoming lectures, we will cover the all the concepts related to coordination chemistry, and in the upcoming lectures, we will cover the entire syllabus up to the graduation level. That means the class 12 students can watch these videos for the concepts. We all know coordination chemistry is an important chapter in chemistry. Very specifically, it is an important branch of chemistry in the inorganic chemistry. So it has very wide applications, and there are many concepts related to the coordination chemistry. So coming to the application of the coordination chemistry, we will discuss in the upcoming classes when we will cover all the concepts related to the chemistry of the coordination compounds. Then after we will better understand what are the chemistry, what is the concept behind the application. But before going to that, I will brief you about the application of the coordination compounds. So there are different fields like in medical field. We all know in the cancer treatment there is chemotherapy. There it has applications in MRI contrast agents, in diagnostic reagents like toxic metals are removed from the body in the chelate therapy. So this is the medical field application of the coordination compounds. And in the industrial application, as catalyst in polymerization, as dyes and pigments in the textile and paint industry, in the fuel cells for hydrogen production and storage. So these are the industrial application of the coordination compound. And in the analytical chemistry, we all know in the analytical chemistry, we do the analysis. That means we detect and estimate the amount of metal, amount of ions present in any specific sample. So there it has the applications in the electronics and material science. We all know the in the conducting polymers and in magnetic materials. So these are the few fields in which there has some applications of the coordination chemistry. And in the finally, in environmental applications, we all know for the purification of water, we know to estimate the hardness of water where the magnesium and the calcium ion concentration is measured, and in the waste management. So these are the very brief applications or brief I am saying because we don't know what are the concept behind these applications. So this is a very brief idea about what are the different fields in which the coordination compounds are used. And after that, we will see where the coordination chemistry started or the history of the coordination compounds. Its history is long back. The first time or the earlier discovery, the first time the coordination compound was discovered. So at that time, it is the 18th century around the first time the coordination compound was discovered, and the compound was Prussian blue. So this compound was used for the painting purpose. So this is a iron-based coordination compound. So this is hexacyanoferrate complex, and outside there are four iron ions. But the chemistry or the modern coordination chemistry started with the Werner's theory. So we can say the development of the modern coordination chemistry started in the late 19th century to the early 20th century when Werner's proposed his theory. So Werner proposed his theory around 1898 or 1893. I am forgetting the year, but for his work he got the Nobel Prize around uh, I think in the 1913 he got the Nobel Prize for this theory. But his theory has some limitations. Let's try to overcome those limitations. Later, there are many theories are proposed, like valency bond theory and crystal field theory and the ligand field theory, which is also known as molecular orbital theory. So these are the theory timeline or the theory line of the coordination chemistry. Just to explain the coordination chemistry, when the first time in the 18th century the first coordination compound was discovered, but at that time the chemistry behind the that compound was sorry were not known, or why it is emitting colors. So there are different aspects of the compound, or there are different aspects of any compound. The chemistry were not known. Basically the chemistry started in the 19th late 19th century when Werner's proposed. Then after it is rapidly and grow in the years. So when we will discuss the upcoming lectures, we will discuss these theories But as the timeline demands, the first theory will obviously be our Werner's theory. So coming to Werner's theory, Werner synthesized some of the uh, coordination complexes, and he conducted some of the experiments on his synthesized compounds. And based on the experimental results, he proposed the theory. So this is the scene of the Werner's theory. But his theory proposed some of the postulates that are even true today. So it has significance. That's why he got the Nobel Prize. So when he synthesized, he taken some of the metals like cobalt, platinum, and chromium. Why he chose these metals only? Because these metals are inert. When we will discuss the reaction mechanism of the coordination compound, that time I will discuss what are the inert complex, what are the labile complex. Inert complex means their rate of reaction is very slow. So that's why it is easy to conduct experiments, easy to observe what are the changes happening. So that's why he chose these metals. These metals are basically inert and they show very slow rate of reaction. So these are the some complexes. The color of the complexes are these. So these are basically some of the complexes on which the experiment were conducted. So that's why I mentioned them here. So these are basically cobalt in the plus 3 oxidation state, and then there are chloride ions and there are ammonia. So in the complex, we will know how the formula are written. So for example, so if this is the coordination compound, then its formula will be somewhat like this. In the when we will discuss the IUPAC naming of the coordination complex, that time I will discuss how they are named or the how we will pronounce it. It's like a hexaamino cobalt uh, chloride complex, or we will discuss later how they are the IUPAC name of the different coordination compounds. But for now, so this is the very brief idea how the coordination compound are written. So coming to the postulates of the Werner's theory, Werner's proposed that the coordination complex can have two type of linkage, or we can say two type of valency. One is primary valency and another is secondary valency. Primary valency is the oxidation state of the metal. That means primary valency shows the somewhere it is the oxidation state of the metal. That is it. And the secondary valence is the coordination number of the metal. What is oxidation state of the metal? What is coordination number of the metal? Okay, we will know when we will take the examples. For now, just remember primary valence is the oxidation state of the metal, secondary valence is the coordination number of the metal. And the primary valence is satisfied by the charged ions, but the secondary valence is satisfied by the neutral molecules, charged ions. Sometimes it also satisfied both by the neutral molecules and the charged ions. The primary valence is ionizable in nature, but the secondary valence is non-ionizable in nature. So these are the postulates of the Werner's theory. He proposed these postulates based on his experimental evidence. Why primary valence is ionizable in nature? Because they are linked with the coordination sphere or the central metal with ionic interaction. We all know ionic interaction means they can be ionized in the solution. But the secondary valency, the ligands linked with the central metal with the coordinate bond, or we all know coordinate bond is one type of covalent bond. That's why they will not be ionized. We all know ionic molecule, for example, NaCl, all the ionic molecules they will be ionized in the solution, but any type of covalent molecules they will not be easily ionized in the solution. But in this case, coordination compound, they will never ionize in the solution. So these are basically some of the postulates proposed by Werner's theory based on his experimental results. Another important point, the primary valency is non-directional in nature. We all know when ion will be present, if a ion or a charge species will be present, there will be electrostatic interaction. We all know electrostatic interaction is from all the direction. There is no specific direction to it, but the covalent bond is directional bond. That's why they have a role in deciding the geometry of the coordination complexes. So this is the postulates, or these are the postulates proposed by Werner's to explain the chemistry or the bonding of the coordination compounds. Important points related to primary valency: it is the oxidation state of the metal, and secondary valency, it is the coordination number of the metal. The primary valency satisfied by the charged ions, the secondary valency satisfied by the neutral molecules or the charged ions or by both. And third, or the important one, primary valency, they are non-directional because they are ionic interactions, so they have no role to play in the geometry. But the secondary valency, they are the directional bond, they have role in deciding the geometry of the coordination complexes. Another point, primary valence is ionizable in nature, but the secondary valence is non-ionizable in nature. Now, how we will represent the coordination complex? I have already mentioned in the slide, but we will know how we will represent the coordination complex, or what are the different parts of the coordination complex when it is written. When we will write the formula, what are the different, here this is the complex, what are the different parts? The entities present inside the square bracket is called the coordination sphere, and it basically represents the coordination complex. So all the chemistry related part, we basically, all the related concepts we will discuss only about this coordination sphere. The outside ion present, here there are three chloride ions. This is counter ion. It is called counter ion. Basically, the role of counter ion is to balance the charge on the coordination sphere. In this particular example, cobalt is present in the +3 oxidation state. That's why the coordination sphere will have the +3 charge on it. Just to balance the +3 charge, there will be 3 chloride ions. We all know chloride ions has a negative charge. So the function of the counter ion is just to balance the charge on the coordination sphere. So this is how we present the coordination complex. Here will be the, where here there will be different examples. So these are the coordination compounds. For example, just focus on the right side. So here the first compound, cobalt with 6 ammonia and outside 3 chloride ions. So in the 12th, I think it is mentioned somewhere that the in the coordination sphere, so there will be ligands, those ligands which will be linked with the central metal with the coordinate bond or the covalent bond. That's why they will be represented with the solid lines, and the outside counter and the here there are the 3 chloride counter ions. They will be represented with the dotted lines. So I think I have read somewhere this, so that's why I presented here. And as there are 6 coordinate bond present in this complex, in the above complex, not below 3 complexes, on the above complex, there are 6 coordinate bonds. That's why the coordination number is 6, or we can say secondary valence is 6. Now coming to different examples. So here there are also the first one, I think the same one. Okay, so there are 3 coordination compounds here. So their formula will be written somewhat like this. Okay, in the first molecule, there will be 3 chloride ions present outside the coordination sphere. In the second, there will be 2 chloride ions, and in the third, there will be only 1 chloride ions. If coming to the primary valency, we all know primary valency is the oxidation state of the central metal. In all the molecules, we don't know how to calculate the oxidation state of the central metal, but okay, just wait for the upcoming lectures. We will know how to calculate the oxidation state of the central metal. For your knowledge, I am saying here all the 3 compounds, the oxidation state of the central metal is 3. That's why the primary valency is 3, but the secondary valency is 6. Why? Because just focus on the coordination sphere, means all the ligands present inside the coordination sphere, they are linked with the central metal with the coordinate bond. That's why in all the complex there are 6 ligands present. That's why they will be linked with the central metal with 6 coordinate bond. That's why the secondary valence is 6. And we know the primary valence is the oxidation state of the metal. How we will calculate? We will calculate when we will have the knowledge of the ligands, what the types of ligand, what are the charge of the ligands. So when we will know those concepts, then we can only calculate the oxidation state of the central metal. Okay, coming to ionization of the coordination complex. When ionization takes place in a solution, we just read that the outside ion or the counter ion present outside the coordination sphere, they are primary valency, or they are they have the ionic interaction. When they will go into the solution, as they are ionic bonds, so they will be dissociated and they will form the respective number of ions in the solution. So for example, just focus on the left side. In the left side, the formula is written. Here there are three chloride ions present outside the coordination sphere. That's why the entire coordination complex means the complex, the hexaamino cobalt complex with three chloride ions outside, when it will ionize, or it will be the solution of it will be make, then there will be four ions in the solution, three chloride ions, and one will be the entire coordination sphere. We all know the coordination sphere will have the +3 charge, and the chloride ion will be the minus charge. There will be three chloride ions and one coordination sphere with positive 3 charge. So total number of ions will be 1 plus 3 will be 4 ions. So this is how the ionization takes place. It is important. When we will take other examples, like here another molecule, here outside there are only two chloride ions, two counter ions, and the entire coordination sphere will be 1 ion. So total number of ions will be 3. And in the second example, there are only one chloride ions present outside the coordination sphere. So counter ion will be one chloride ion and the entire coordination sphere with +1 charge. So that's why there will be two ions only. So here two ions. So it has some applications when Werner conducted some of the experiments, like conductance measurement. There are so from these number of ions you can predict the formulas of the coordination complex. So we will discuss. Coming to the experimental evidence, Werner synthesized complex and done some of the experiments, and from the experimental results he got the idea of the bonding. Okay, so coming to the first conductance experiment. So for this, we know conductance of any solution will be directly proportional to the number of ions. If a solution having more the number of ions, then it will have more conductance. So for this we have taken, for example, three container. In the three container there will be three molecule, three coordination compound, or three coordination complex. Just focus on the three coordination compound. In the first, it will have four ions. Am I correct? Yes, because the outside there are three chloride ions and one is the coordination sphere. In the second container there will be three, there will be total number of ions will be three, two chloride ions, one is coordination sphere, and in the last container there will be only two ions because one chloride ion and one is the coordination sphere. So total number of ions in the first container is 4, in the second container total number of ions will be 3, and in the last container the total number of ions will be 2. So naming the systems A, B, C, and the total number of ions 4, 3, 2. So we all know conductance is directly proportional to the number of ions. That's why the first container, it contains 4 number of ions. So the conductance of the first container solution, if we take the molecule of the we molecule mentioned on the first container and make the solution, and in the solution there will be 4 ions. That's why the conductance of the first container will be higher than the second one, and the second one's conductance will be higher than the third one. So the conductance order will be A greater than B greater than C. Okay, coming to precipitation measurement. So we will take one molecule of the coordination compound, the same molecule. I think I am repeating this molecule again and again. In this molecule there are three chloride ions present outside the coordination sphere. So this is the molecule. When we will measure the precipitate, when we will take the solution of this complex, so in the solution there will be ionization. So when it will ionize, there will be three chloride ions and one coordination sphere with positive 3 plus 3 charge. So when there will be three chloride ions present in the solution, when we will add excess amount of silver nitrate solution to it, we all know in the 12th level, I think we do the test for the chloride ions or the halide ions by taking the silver chloride solution. When it will treat with the chloride ions, or the chloride ions will react with the silver nitrate solution, it will form the silver chloride precipitate, which is white in color. So as in the solution there will be three chloride ions, so when it will be treated with the excess amount of silver nitrate solution, it will only form three silver chloride precipitate, because here in the solution we will have only three chloride ions. That's why only three precipitate, or the three number of silver chloride precipitate will be formed. I think I am clear. The number of chloride ions present outside the coordination sphere, the same number of precipitate silver chloride will be formed. That means in the equation, if we take one molecule of complex with three chloride or three counter chloride ion, then we will have three molecules of silver chloride precipitate when it will be treated with the excess AgONH3. Okay, now the precipitation is clear. So when Werner conducted the experiment, taking the complex in the solution, and then after adding excess silver nitrate solution, he got the three molecules of silver chloride precipitate. So from that we can assume that, so we know the entities present outside the coordination sphere will be available in the solution as the ion form. So here we are getting three molecules of silver chloride precipitate. That means the in the complex there will be three number of chloride ions present outside the coordination sphere. From that we can have the idea of the formula of the coordination complex. So now the precipitation experiment is clear to everyone. Now we will take some more example. Here 1 mole of, if we in the previous experiment we just take the one molecule, but here we are taking 1 mole of that specific complex, where if in the 1 mole of this complex will be taken, what is written in the left side, then we will get 3 moles of silver chloride, because in 1 mole of the complex there are three chloride ions present. So that's why the three chloride ions will react with the silver chloride solution, because silver nitrate solution, because the silver nitrate solution present in excess. So when the excess silver nitrate solution will be treated with the three chloride ions, they will form 3 moles of silver chloride. So if we take, for example, 3 moles of the same complex, then we will have in the solution, then we will have the 9 number of chloride ions, isn't it? Because in the 1 mole we are getting 3 chloride ions. In the 3 moles of that specific complex, we will get 3 into 3, 9 moles of chloride ions. Is it clear to everyone? In 1 mole of that specific complex, in which 6 amino is inside, and the only I am focusing on the outside coordination sphere ions. That means in that complex there are three chloride ions present outside the coordination sphere in 1 mole. If we take that same complex 3 moles, then obviously we will get the 9 number of chloride ions. So when 9 number of chloride ions will be treated with the excess silver nitrate solution, we will get 9 moles of silver chloride precipitate. So now this is clear to everyone. So there are numericals related to this concept, so understand it. Sorry. And we are taking another molecule in which there are two chloride ions present outside the coordination sphere. That's why when we will take 1 mole of that specific uh, complex, we will have 2 moles of silver chloride solution. And if we take 5 moles of that specific coordination complex, then we will have 5 moles. In each mole there are 2 chloride ions. In 5 moles there will be 10 chloride ions available in the solution. And when we will treat with excess silver nitrate solution, excess means there are excess amount of silver nitrate solution. That means excess amount of silver ions, excess amount of nitrate ions. So excess amount of silver ions, it will react with only 10 mole of 10 mole of chloride ions, and it will form 10 moles of silver chloride precipitate. So from this precipitation we can have an idea of what will be the formula of the that specific coordination complex. So now the precipitation is clear. Now the conductance is clear. Conductance is directly proportional to the number of ions. The coordination complex, which will have the more number of ions, that specific complex, when the solution of that specific complex will have more conductance comparing to others. So now the precipitation is clear. The number of chloride ions or the number of bromide ions present outside the coordination sphere, basically whatever the ion present outside the coordination sphere, that will be available in the solution. So for the precipitation, here we are taking the example of chloride, and that's why we are taking the um, excess amount of silver nitrate solution, and it is reacting, and it is forming the silver uh, chloride precipitate, which is white in color. Now the precipitation is clear to everyone. Now these are the some questions you can go through the lecture and understand the concept and try to solve it out. So thank you all for today's class, and just revise the concept, make notes. I will suggest you just go through the textbooks, because without the textbook you can't have the entire sum of knowledge in the textbook. There are different types of examples. Solve it and grasp the concept, then follow the upcoming lectures. So thank you for today's session.